slightly late to the party, but also I wanted to make a video about state space models, or S4, S5, S6, S/Mamba, as you may have heard of them before. This modeling framework that can be seen as an alternative to attention. So the setting that we are working in is the following. We have this sequence U consisting of capital L elements where every element is d-dimensional. The task that we're interested in doing is the classic predict the next value, or like next token prediction, or even classifying the sequence. And one assumption that we make is that L, the sequence length, can be very large. Why is this an assumption of interest? So you may have seen this kind of like battle of the context windows with models that are coming out, allowing you to process increasingly large context lengths or prompts, with, I believe, most recently Gemini 1.5 Pro allowing a context window of 1 million. And this allows you to do kind of like cool new things. Like, for example, you could drop in, as this paper shows, a 1-hour YouTube video with a compilation of, in this case, 500 different clips, and ask very specific questions about what happened in this YouTube video. And if the model is processing this whole long context window correctly, it will actually also be able to give you correct answers to what are very detailed things that happen. One small caveat to the ability to process these long context windows is that this paper loss in the middle shows that even if it can process it, it doesn't necessarily mean that it uses all the information in the context. So specifically, they show that if crucial information is placed somewhere, let's say in the middle of your context window or context length, then the model is not always able to correctly retrieve that information, as opposed to, if you place it in the beginning or in the end, it is much better able to do so. These results are on GPT 3.5, so slightly outdated, but still an interesting observation. The other thing to note is that besides obviously performance, we are interested in a computational complexity per layer that is going to be low, and ideally we also want processes that process this sequence that are highly parallelizable, aka the number of sequential operations we want it to be small. Okay, let's go a few model architectures back and talk briefly about the recurrent architecture that is a classic method for processing time series. What does this method do? Basically, in order to compute the prediction, the Y output at time t, it looks at the current input at time t, as well as the hidden state that the model computed. And this hidden state kind of compresses all the information of the previous elements in your sequence inside of it. So in principle, this should allow you, whenever you're making your prediction at time t, to also look back on all the other events or information that happened before. The good and bad about this kind of architecture. So the good is that we have this computational complexity per layer of this recurrent architecture that is linear in terms of the sequence length L. It is, to be precise, order L d squared, with d again this dimensionality of our inputs and also hence of our matrices W. And also this leads to kind of this cheap autoregressive inference. Why? Because whenever we make our prediction yt, we are in principle only looking at this hidden state that has summarized all the information from the past. So we don't have to look over all the elements. We're just looking at this hidden state, and that's what we're using to make our prediction, resulting in both cheap memory and cheap computational cost whenever we are making this one step ahead predictions. And then the bad things. So inherently, this kind of model is very sequential. In order to compute the current hidden state or the current output, we also need to have computed all the other ones in the past. And hence, it's not trivial to parallelize it. There have been a few papers that make some approximations in order to still parallelize it, but it's not the natural thing to do for this kind of architecture. And the other thing that you may also have heard about these models is that they struggle with long sequences due to the problem of the gradients vanishing. So the gradients, if we're looking to predict time t, might no longer properly propagate, let's say, information from the past, allowing us to not properly use that information, essentially. Okay, and then of course we had this big success of using attention when processing sequences. So let us very quickly recap what attention does. The classic self-attention operator basically computes the following. it would compute 3 projections of our input U, a projection with a matrix WQ, a matrix WK, and a matrix WV, in order to give us the query, key, and value elements. What it then does is it kind of, if we look individually at each element of the query and the key, it would compute a dot product or this kind of similarity metric between them, and doing this for every possible combination of elements, giving us this L by L matrix, which we then scale by the square root of the dimensionality of each of our inputs, pass it through a softmax, and then multiply it with the value vector that we had, the value matrix, sorry. If we look at the dimensionalities, again, each of these projections will be of dimensionality capital L, sequence length, times D, the dimensionality of each of our individual elements. And if we look at this as a whole, you can basically look at this, whatever happens inside this softmax, as being this matrix T of size L by L, matrix that also depends on our inputs U. And that is the matrix that we then use to multiply with our U times the W, this value projection. Small note to make is that here I'm not using any masking, so if you would want to ensure causality, you would also have to be masking this matrix T. We don't typically work with just a single attention operator. We would actually use H, the number of heads attention, where we would concatenate all the outputs from these H attentions and use these to then compute our final predictions. And one thing to note is that also here we would not be working with matrices that would be D by D dimensional as we did before. We would also make the matrices slightly smaller. We would be working with matrices that are D by DK dimensional, and DK is D divided by the number of heads that we're using. So kind of smaller matrices that we use to project our inputs, but more of them which we then concatenate in order to compute our outputs. A visualization on what attention basically then does. This is for a single head. The output on the left would be computed by this matrix that would be applied to our input on the right. So it's kind of easy to interpret what it does, in the sense that every element of the output, by looking at for which attention weights is the value high, we can also then see which are the input elements that this prediction looks at. So what are the input elements that are most important whenever predicting a particular element in our output sequence. And the other nice thing here is that this matrix, again, it was dependent on our inputs itself. So basically where in the input the attention map looks in order to compute the output depends on the input itself. So this results in this relatively rich modeling capability, because again, we're firstly looking over all possible sequence elements that we had, but also where we look depends on the current sequence that we're actually considering processing. So whenever we compute attention, we are basically doing a lot of these matrix multiplications. So we're multiplying these L by D matrices by D by L, L by L by D by L, blah, blah. And the good thing is that matrix multiplications are in principle highly parallelizable. Specifically whenever we are training and whenever we are mapping like a whole sequence directly to another whole sequence, we can quite nicely parallelize this whole procedure. And then techniques such as flash attention and flash attention 2 have made these computations even more efficient by cleverly using like the memory of the GPU. And what is the bad thing of it though, is that again, we are still multiplying these matrices that are all have a size of L by L, L by D, blah, blah. So in terms of the computational cost of multiplying, it is going to be squared in the sequence length. And then if the sequence length is going to be very long, then basically both training, but also specifically inference can still be very expensive. So whenever we want to predict a single element, we will still be looking at the whole path, still be working with these L by L matrices, which will make the computational costs whenever we do a one step ahead prediction quite high for long sequences. And then that is kind of where state space models come in, because the core promise is we would like to combine this parallelizability of transformers, so use operations that we can parallelize very nicely in order to be able to process sequence to sequence operations fast. So leading to fast parallelizable training when we have all the sequences already kind of at our disposal. But we would like to combine this with the memory and also the computational efficiency of recurrent neural networks, which whenever we would be doing like this one step ahead prediction, we don't necessarily need to have these expensive order L squared operations, but we could have it basically cheaper. Okay, so the general formulation of a state space model is the following. We have x prime of t given by this equation with matrices A times x, matrix B times u, and then the output sequence y is computed as this c times x plus d times u. Basically what happens here is that we have our input u. This is projected by this matrix B, which has size h by d. H is the size of our hidden state x, and this hidden state x is then used to compute the output by multiplying it with c, which is d by h, and also again the input is added in there through this matrix D, which is d by d. Whenever we want to work with this, we would discretize this equation, so we would get basically that the hidden state at time k is computed by this A bar matrix times the hidden state at the previous time point plus b times the input bar b at the current time step, and then the output is again bar c times the hidden state plus d bar times the input. So you can kind of see also a relation to recurrent networks, right? Like it's like basically this is a linear recurrent neural network. Different discretizations are possible. We can use this bilinear discretization, which would lead to a particular form of our matrices. Specifically also note this discretization parameter delta. We could use this zero order Holt discretization, giving the following forms for the matrices. And again, as I already hinted at, we have a nice recurrent representation. So basically our inputs are all getting projected into this hidden state x, so that whenever we are making a prediction at our current time points, so whenever we are outputting yk, we don't need to directly look at the whole sequence in the past like attention did, but we are simply working with the current input element and the hidden state, which in itself already contains kind of like all the information from the previous inputs. So this leads to fast inference, which was one of the goals that we wanted to have. A small side note is that I do want to draw another parallel between these models and attention, which is by noting that if we rewrite the hidden states more explicitly and also then the outputs more explicitly, what we can then actually find is that it also does this kind of input-output mapping through this matrix T. In attention, this matrix was dependent also on the inputs, and here it would be actually independent of the inputs, but consisting of all these different state space model matrices A, B, C, and their products. Now we could also use this kind of matrix vector multiplication to then directly, when we have available the input and the output sequences as we have during training, we could use this formulation to compute fast sequence-to-sequence computations. So we don't necessarily want to be working with this matrix vector product, because then we would remain having this order L squared computational complexity. So what we can actually note is that we can also rewrite our output as a convolution of the kernel k bar with our inputs. Now this kernel k bar is given by the following. It's given by these products of the matrices A, B, and C, our SSM matrices discretized. So the size of this convolutional kernel will actually be the same size as our input sequence length. But the nice thing is that with convolutions, we have the fast Fourier transform, which then allows us to decrease this computational complexity of order L squared that we had with the matrix vector multiplications to this order L log L. This assuming that we are already given our convolution operator bar k. So to summarize this for now is that we are happy with the convolution view, because whenever we are training, so we have both, we're interested in computing the whole sequence y in one go. We can do this using a subquadratic complexity as opposed to this L squared complexity that attention would give us. At the same time, we had this state space model / recurrent view that would give us this fast autoregressive generation because we kind of decoupled the complexity from the sequence length. So unlike in attention where to compute the current output, we would need to look back over the whole sequence and multiply these big L by L matrices. Here we are only working with the hidden state size, which is H and hence also easier to work with. How would this layer be placed inside a neural network? Basically, we would do the following. So we would have a hidden layer, which has UK as the output from some previous layer and computes YK as the output from the current layer, aka the input into some next layer. We would apply the standard nonlinearities after the output is computed, normalizations or some MLPs as well. And the thing that we would be learning in this model is that we would be learning the parameters A, B, C, D, as well as the step size or the discretization parameter delta that we had when we went from the continuous time system to the discretized one. Okay, and then we are ready to define S4, because basically there are three things that I did not yet talk about when introducing state space models. The first thing is that remember that I worked with saying like, okay, let's just assume that the dimensionality of each input sequence is 1. So how do we use it on multiple dimensions? The second thing is how do we initialize the matrices that we learn with? And how do we actually compute the kernel efficiently? So I said once we have the kernel, we have this nice order L log L computational complexity, but how do we actually get the kernel? So these are the three kind of innovations that S4 introduces. Okay, so first things first, how do we process multiple dimensions? Basically, we do the following thing. We apply an SSM to each dimension of the input kind of independently. So basically, each input dimension gets mapped into an H-dimensional hidden state and consequently also gets mapped into a one-dimensional output. We apply a nonlinear activation function to this, and also the way we would then mix dimensions, because here for now we have been only independent in all the dimensions, is that we would compute kind of like a linear mixing layer MLP in order to combine all the input dimensions in order to give us our final output sequence. And the trainable parameters for this kind of setup would be, again, our matrices A, B, C, and D, and our discretization parameter, but we would have D of each of these matrices because we're using a single SSM layer for each of the dimensions that we have. So in terms of a visualization, which I took from the very nice S5 paper, basically we would be processing each dimension in the input individually. So if we rewrite this into a big matrix A, we would essentially have D times these H by H blocks that are being applied to the hidden state. If we rewrite our bit matrix B as a big matrix, we would have H by 1 blocks that are being applied to each dimension of our inputs. We would compute our output where we would have these D1 by H blocks. We would pass it through this nonlinearity and we would have this mixing layer that is the only part of this model that would actually mix in the dimensions as well. So the other parts mix in terms of the sequence, and this is the part that would mix also in terms of our dimensions. Okay, then we get to the second point, which is how do we actually initialize the matrices? The point here is that prior work, these two papers, for example, below discuss this, found that if we just initialize each of these matrices randomly, we don't necessarily get good performance. What could be a possible explanation for this? So if you look at the solution to this state space model, you get a kind of like exponential function structure, which would also mean that the gradients would have this exponential structure, and specifically they would scale exponentially in the sequence length, potentially leading to, again, the same problem with recurrent nets, this vanishing or exploding gradients and the inability to model these kind of long-range dependencies to remember longer things from the past. So the S4 paper then proposes this kind of Hippo initialization where the Hippo matrix A is given by the following setup. Every element of this matrix is given by this configuration that I show here. Why does this work? Or at least how is this introduced in the original paper? The paper motivates it from a kind of like optimal compression perspective. So it says, suppose that we have this signal, our input U, consisting of these capital L elements. What we would like is we would like to compress it into this hidden state such that this hidden state contains all the information needed to reconstruct the signal as good as possible. Basically, we can understand this a bit better by then approximating the signal by a decomposition into basis functions, specifically orthogonal polynomials with coefficients given by some xt's. And then what the paper notes is that if you actually kind of approximate the evolution for these coefficients by an ordinary differential equation, you would get a state space model representation for the coefficients xt, which we now see as the hidden states, where this matrix A that defines the evolution of the hidden states would actually be given by this Hippo matrix, as I present there. And the Hippo initialization improves the performance quite a bit. So for example, as quoted from the original paper, on sequential MNIST, we go from 60% to 98%. Okay, and then we get to the third problem, which is how do we actually efficiently compute the kernel? Remember again, convolution view, we liked it because we could rewrite the output sequence as a convolution with the kernel bar k and the input sequence, which we could compute in this order L log L computational complexity using the fast Fourier transform. But what is actually the computational complexity of computing the kernel bar k itself? So naively doing so would require us to multiply L times, because we have L elements in our convolution kernel, and with an H by H matrix, our matrix bar A, so leading to a total computational cost of order H squared times L. How can we circumvent this computational complexity? So one thing to note is that suppose we had a diagonalized form for A available, then if we would define a system that uses, instead of A, the diagonal components, so the matrix lambda, which has on its diagonal the eigenvalues of A, then basically the state space model using this x tilde would be a reparametrization of the original state space model that we had. So in principle, we could just work with this matrix lambda instead of the original matrix A if this diagonalization of the matrix A would be possible. And this is something that we like because for diagonal matrices, the computation of the kernel could be done a whole lot more efficiently, specifically, again, as very nicely explained in the original thesis that introduces S4. It would need this order H plus L times log of H plus L computations using this Vandermonde product setup. Okay, so again, if we had a diagonalization of the matrix A, we could use the diagonalized representation of the state space model and basically be working with, instead of a full matrix A, with only a matrix with elements on the diagonal. Remember also that we said in order for the model to properly learn, we would need this Hippo initialization. And then we get to the unfortunate thing, which is that a naive diagonalization of the Hippo initialization for A does not necessarily work because, again, as is derived in the thesis and in the paper, you would have entries that are exponentially large in the state size H, which would not lead to a stable discretization. So instead, the authors note that you could rewrite the Hippo matrix A as a sum of two matrices, a normal matrix and a low rank matrix. And then the observation is that the normal component of this rewrite can actually be stably. So then we get to the final formulation of the setup. We would basically have as trainable parameters now this diagonal matrix lambda, where we would train both the real and the imaginary parts. We would have matrices P and Q, which come from this low rank second decomposition of this Hippo matrix. We would still have as trainable components, of course, our matrices B and C. For initialization, what we would do is we would initialize this lambda to a matrix with the eigenvalues now not coming from A, but coming from the normal part of this decomposition. So basically from this part here, because that was the part that could be stably diagonalized. We initialize to that, and from there we train. Question is that for this kind of like normal plus low rank decomposition, can we still efficiently compute the kernel, the convolution kernel that we are working with? And as the authors introduce, yes, we can. It would still have the same complexity as the complexity would be for a diagonal matrix with a somewhat more involved algorithm as given here. I won't go into the details, but basically point is it is possible. Now, I like simple things. So then the question that I would naturally have is that, is it possible to completely like forget about this low rank part and only work with the normal parts and use as initialization of our lambda only just like the diagonal elements and completely forget about these terms P and Q that came from this second term, the low rank part of our decomposition. As a more recent result states, so this paper on the effectiveness of diagonal matrices, actually, yes, it might be possible. So diagonal state spaces could be just as expressive as general state spaces, as this paper again shows. The only thing is that you need to kind of more carefully keep an eye on the elements of your matrix lambda. So specifically, as this paper notes, the real parts of the elements of this matrix lambda could become positive during training, making training unstable on long inputs. So one of the things the paper then proposes to do is says, okay, let's just try to restrict the real part of the elements to always be negative using this kind of restriction given here. And that, as the paper shows, the results can be quite good. Okay, this was S4. Basically, using a state space model, individually for every input dimension, we use a separate state space model. The mixing of the dimensions is then done using an MLP layer in the end. The computation of the output sequence is done efficiently using this convolutional operation, and the only thing that we need to take care of there is that we can also compute the convolution kernel itself effectively, which we can for diagonal or diagonal plus low rank decompositions. So then S5 proposes to, instead of having a single SSM for every dimension, it says let's just work directly with all the dimensions of the input that we have. And instead of using this convolution operation, it uses something known as the parallel scan algorithm. So quickly on parallel scans, basically what would a parallel scan be? Suppose that we are given this binary associative operator, meaning that the operation between A and B and then C is the same as first B and C and then A. Then basically the scan operation, in some literature it's also called the all prefix sum, would return you L elements that are computing this operation between A1, A2, A1, A2, up to L. How is this useful for state space models? If we define this associative binary operator in the following way, so given this tuple A0, B0 and a tuple A1, B1, then basically the operation computes this thing. What we can then note is then if we compute the same operation for A0 multiplied up to AK minus 1 and XK minus 1, so the hidden state at our previous time point, and we compose this using this operation with a tuple that has AK and BK times UK, the inputs at our current time point, we would basically get this product of the matrices and our current hidden state. And then if we apply this scan operation over all of our sequence elements, essentially we would get this guy for all of our time points. So we would have the hidden states for all of our time points up to capital L. And the additional benefits for using then this kind of setup is that we can also work with time varying or even more so input varying matrices, which we will get into in a bit. And the reason we like this algorithm is clearly because we can also parallelize it very effectively. For more details on that, there is this nice explanation of NVIDIA on how to compute this effectively in CUDA. In terms of the computational cost, so for a general matrix A, the computational cost would actually be cubic in terms of the hidden state size H. However, if A is again somehow structured, or in other words diagonal, then we would only need this order H times L number of operations. Why did the original S4 paper not apply this parallel scan algorithm? Why did they look at the convolution? So because again, S4 considered each dimension individually, applying it to actually all D of the h-dimensional state space models would be more expensive than the convolution approach that S4 uses. Okay, so basically in S4, what we did is we would have applied D independent state space models to every dimension of the input. We also refer to this as this multiple single input, single output system. And here with S5, we consider all dimensions kind of at the same time, resulting in this multi-input, multi-output system, where the big changes are in how we use the matrices B and D. So B is now a H by D dimensional matrix, and D is a D by D dimensional matrix. So again, it's in this operation, we are already directly mixing all the different dimensions of our inputs in order to compute the hidden states and also then to compute the outputs, unlike S4, which would do it independently for each dimension and only later on mix the dimensions through this MLP layer. So if we look at the hidden state size differences, basically for S4 or this CISO formulation, we would have effectively a hidden state size of D times H, D times an H dimensional hidden state. And for the S5, we would just be working with this H dimensional hidden state, which could be clearly significantly smaller and hence also allows us to actually effectively apply the parallel scan algorithm. And another benefit, as I already said, is that since we are already directly mixing all the dimensions through the matrix B and through the matrix D, we also do not need this additional MLP mixing layer that S4 was using. Again, a nice visualization from the S5 paper, but basically here we are working with kind of these dense matrices A, B, and C. Again, forgetting about D because D we would just model as a residual connection. Unlike the S4, where these matrices had this kind of like sparse diagonal block structure, here they are dense and having size H by H, for example, instead of HD by HD as the A would have in the S4 formulation. All right, final model, S6. What is the core feature if we think about attention versus S4 and S5 that attention does have, but S4 and S5 don't have? Remember that I said that with attention, the nice thing is that if we look at kind of this operator map, wherever the matrix or this operator map looks at in terms of the input sequence depends on the input sequence that we are feeding in itself. So we kind of have this like input dependency that determines which sequences are we looking at in order to compute the output. For S4 and S5, this is not the case. So if we, again, remember this formulation in terms of Y is T U, where T was this matrix that we computed for this state space model using all these products of A, B, and C. This is fixed. It's fixed kind of forever over our whole time. In other words, whenever I get in a particular element or a particular sequence, it doesn't change. So we don't have this input dependency that attention has. So what does S6 do? Core idea is basically improve state space models by also adding in this input dependency or what they call selection. The reference for this would be the Mamba paper that I link below. Let's look at the formulation. The formulation is very simple. Before, again, we had this setup with matrices A, B, C, and D, the state space formulation, where what we had as trainable parameters were the matrix A, B, C, and D, and also the discretization parameter delta. Now, what we actually do is we replace the matrix B by a linear layer that maps U into our hidden state size. We also replace C by a linear layer that maps U into a hidden state size, H. And also the same thing for the delta parameter. So the delta parameter now also becomes a linear mapping from U into something that in this case is of dimension 1. What changes in terms of these trainable parameters? So we still have as a trainable parameter the matrix A, we do not change that. Now we would have as trainable parameters in the matrix B, not the elements of B directly, but the weights that would map input into our output matrix B. Same thing for C, the trainable parameters become the weights that define this linear mapping. For D, nothing changes, and for delta, again, same thing, we would have the trainable parameters coming from this linear mapping that maps input into a one-dimensional output, but also sometimes they denote that they have an additional kind of like bias term that is also trainable. Again, in terms of a visualization, basically the input at time k gets mapped through 3 different linear layers to compute the matrix B, the matrix C, and to compute our delta discretization parameter. One thing that you might wonder is why is actually the matrix A not also an input dependent matrix, because the matrix A seems relatively important because it kind of tells us, what do we carry on from the hidden state from the previous time point into the hidden state of this time point. Why is this not selective or input dependent? If we use this zero order hold or ZOH discretization, then basically the dependence of A bar, the discretized variant of A, is only on delta. So making delta dependent on the input is kind of enough, or this is what is argued by the authors. Okay, nice. How do we actually compute things efficiently here? So remember that before, in, for example, like the S4 formulation, we had that yk could be given by this summation over the products C times a particular power of A times B plus potentially this matrix D, which is only added for the input elements whenever k is equal to n. Now things change a bit, because in this case, this C matrix, the B matrix, they become state dependent, or in this case, I just denote it with this time varying element k, in the sense that they change depending on which element of our sequence we are considering. And this is the problem, because we can no longer pre-compute all matrices in an effective way due to this kind of input dependency. We kind of have to wait for the input from the previous processing time step in order to compute the current matrix, because it's matrix C and B, because they're going to be dependent on that. So we can no longer kind of leverage this convolutional computation. But luckily, as we had before, we introduced this parallel scan algorithm that can actually still be applied to this current setup here, so that we can still compute the direct output sequence very efficiently. And another thing to note is that the other innovation in the paper also comes from cleverly using the memory on the GPU in order to parallelize or make the parallel scan implementation even more efficient. Okay, this is it. I want to summarize in kind of like some very kind of core differences. So remember again that I rewrote the input-output mapping all the time also through this operator T. So what is then the core difference between attention, S4, S5, and S6? The differences are in basically how they mix the sequence length and how they mix the element dimensionality itself. For example, S4 would consider the input dimensionality separate until the final processing through this mixing layer, while S5 would mix them directly. The other difference would be whether T is input dependent or not. In attention and in S6, yes. In S4 and S5, no. How do we actually initialize the matrices? In attention, we kind of just standardly initialize them, while with S4, S5, and S6, we use this Hippo initialization. And finally, a smaller kind of difference is also what is actually the structure of T. So how, what are the structures of the different components of this operator T that we have? That's it. Thank you.